Welcome to a lecture series on food technology. Today we are going to talk on chromatography. Coming to introduction. At the beginning of the 20th century, the Russian botanist Mikhail Tsvet invented and named chromatography. He separated plant pigments by passing solution mixture through a glass column packed with fine particles of calcium carbonate. The separation of those pigments appeared as colored bands on the column. Tsvet named this separation method for the two Greek words chroma and graphene, which mean color and to write respectively. In the past 6 decades, chromatography has been extensively applied to all branches of science. The 1952 Nobel Prize in Chemistry was awarded to A. J. P. Martin and R. L. M. Singe for their contribution to chromatographic and separations which tremendously impacted chemistry-related sciences. More impressively, between 1937 and 1972, a total of 12 Nobel Prizes were based on work in which chromatography was a key tool. In all chromatographic separation, the sample is carried by the mobile phase, which may be a gas, a liquid or a supercritical fluid. The mobile phase is then percolated through an immiscible stationary phase that is fixed on a solid substrate. When the sample passes through the stationary phase, species are retained to the varying degree as a result of the physico-chemical interaction between the sample species and the stationary phase. The separation of species appears in the form of bands or zones resulting from various retentions. Chemical information can thus be analyzed qualitatively and or quantitatively on the basis of these separated zones. Based on the physical means by which the stationary phase and mobile phase are brought into contact, chromatography can be classified as planar or column. In planar chromatography, the stationary phase is supported on a flat plate or a piece of paper, while the mobile phase is usually driven by capillary force, gravity or an electric field. In a few cases, the mobile phase is forced under pressure, for example, in overpressure planar chromatography. When a tube holds the stationary phase, the chromatographic method is referred to as column chromatography. In column chromatography, the mobile phase is driven by pressure gravity or an electric field. Because of its astonishing separation power, column chromatography has become the most frequently practiced means of analytical separation. 3 types of mobile phases are used in column chromatography, that is liquids, gases and supercritical fluids. Among these 3 types, liquids are the most frequently used. Therefore, liquid chromatography is the predominant technique used in modern analytical separations. Early liquid chromatography was operated in glass columns and the mobile phase was driven by gravity. To ensure a reasonable flow rate, the column was packed with large particles in the 150 to 200 micromolar range. Such packing yielded poor results with long separation times, often several hours. Beginning in the late 1960s, small particles were packed in a steel tube which was subjected to high pressure. Such a system dramatically improved the separation power of column chromatography. In the early years, HPLC stood for high pressure liquid chromatography. 3 to 10 micrometers particle diameter are commonly used as stationary phase in HPLC. Separation can thus be done in a high performance mode, which means high resolution and short analysis time. Therefore, these newer procedures are termed high performance liquid chromatography to distinguish them from the earliest methods. Coming to basic chromatographic terminology. Chromatograph, which means instrument employed for a chromatography. Stationary phase, phase that stays in place inside the column, can be particular solid or gel based packing or a highly viscous liquid coated on the inside of the column. Mobile phase, which means solvent moving through the column, either a liquid in liquid chromatography or gas in gas chromatography. Eluent, which means fluid entering a column. Elute, fluid exiting the column. Elution, which means the process of passing the mobile phase through the column. Chromatogram, which means graph showing detector response as a function of a time. Flow rate, which means how much mobile phase passed per minute. Linear velocity, which means distance passed by mobile phase per 1 minute in the column. Bed volume is the total volume inside the column. Void volume is the volume of solution not trapped in the beads. Internal volume is the volume of solution trapped in the beads. Volume of the gel matrix is Vt equal to V0 plus Vi plus Vg. Elution volume is the volume necessary to elute a substance from the column. Coming to general principles of chromatography. The partition principle. The partition chromatography, when a solute is allowed to equilibrate itself between two equal volumes of two immiscible liquids, the ratio of the concentration of the solute in the two phases at equilibrium at a given temperature is called the partition coefficient. A mixture of substances with different partition coefficient can be quantitatively separated by a technique known as countercurrent distribution, which is first developed by L.C. Craig, in which many repetitive partition steps take place. Coming to partition chromatography, partition chromatography is a logical extension of the countercurrent partition principle for achieving chromatographic separation of mixture. The technique, originally developed by A.G.P. Martin and R.L.M. Singe, has since been applied to an enormous number of separations. The separation is achieved in a huge number of partition steps, which takes place on microscopic granules of hydrated insoluble inert substances such as starch or silica gel packed in a column or layered on a plate, or the granules of cellulose in paper. The granules, through inert, are hydrophilic and as such as surrounded by a layer of tightly bound water. This tightly bound water, since it is immobilized, serves as the stationary phase. On the surface of this stationary phase flows the mobile phase of an immiscible solvent containing the mixture of to be separated. The solute molecules are subjected to microscopic partition process between the immobilized water layer and the flowing solvent. Since the process takes place on the surface of each granule, the number of partition steps is so great that the substances move along the column or surface at a different rate as the mobile phase flows through it. The principle of partition is exploited in gas or liquid chromatography, that is GLC technique also. Separations depend upon the partition of the solute molecule between a liquid supported on a suitable solid and the gas flowing through the system. In true partition chromatography, the only factor which influences the movement of a compound as the solvent travels along the stationary of that compound in the two phases. Substances more soluble in the mobile phase will migrate greater distances as compared with the substances more soluble in the stationary phase. Other compounds of intermediate solubility between the two phases will migrate to intermediate distances depending upon their partition coefficient. Coming to adsorption chromatography, substances differ in their adsorption desorption behavior between a moving solvent and a stationary solid phase. This behavior of substance can be exploited to achieve its separation. Adsorption is a surface phenomenon which signifies a higher concentration at an interface as compared to that present in the surroundings medium. Adsorption should not be confused with absorption, which signifies the penetration of one substance into the body of another. For the purpose of chromatography, the term adsorption has limited meaning. It usually denotes interaction involving hydrogen bonding and weaker electrostatic forces of the substances with the adsorbent. The solute molecule which interacts more with the adsorbent, which is also the stationary phase, is retarded more, while less interacting solute molecules are retarded less. In this way, a separation of sample components is achieved. Coming to ion exchange chromatography. This procedure was first developed by W. Kohn and may be defined as the reversible exchange of ions in solution with ions electrostatically bound to some sort insoluble support medium. The ion exchanger consists of an inert support medium coupled covalently to positive or negative groups. To these covalently bound functional groups are bound through electrostatic attraction oppositely charged ions, which will be exchanged with like charged ions in this sample. Thus, if anion exchange chromatography is performed, negatively charged sample components will interact more with the stationary phase and will be exchanged for like charged ions already bound to the matrix. These sample ions will be retarded, whereas other uncharged or positively charged ions will not be retarded to the same degree and will be eluted out fast. The situation will be exactly reversed for cation exchange chromatography. Coming to gel filtration chromatography. This technique exploits the molecular size as the basis of separation. The support medium, a gel, consists of porous beads where pore size is strictly controlled. Macromolecules smaller than the pores get entrapped in the pores and move very slowly, while those bigger than the pores travel unhindered through the column. Thus, the main interaction between the solute and the stationary phase is with respect to the size, and this is ultimately the basis of separation also. This technique is also used to determine relative molecular weight of an given macromolecule. Coming to affinity chromatography. The technique utilizes the specificity of an enzyme for its substance, also receptor for its agonist antibody for antigen or substrate analog for enzymes, that is other than proteins with biological specificity separation. A substance analog is coupled to the gel matrix and the cellular suspension is allowed to percolate through. The enzyme, which is specific for the substrate analog, binds to the gel, becoming immobile while all other components move down and out. The technique has high resolution power. The table shows various types of chromatographic technique. Coming to paper chromatography. In paper chromatography, the mobile phase is a solvent and the stationary phase is water held in the fibers of chromatography paper. Solution of the mixture to be separated is spotted onto a strip of chromatography paper with a dropper. The solvent moves through the paper due to capillary action and dissolves the mixture spot. The components of the sample start to move along the paper at the same rate as the solvent. Components of the mixture with a stronger attraction to the paper, that is stationary phase, than to the solvent will move more slowly than the components with a strong attraction to the solvent, that is mobile phase. The difference in the rates with which the components travel along the paper over time lead to their separation. Particular mixtures will have chromatographic patterns that are consistent and reproducible as long as the paper, solvent and time are constant. This makes paper chromatography a qualitative method for identifying some of the components in a mixture. Coming to principle of paper chromatography. This technique is a type of partition chromatography in which the substance are distributed between two liquids, that is, one is stationary liquid which is held in the fibers of the paper and called stationary phase, and other is the moving liquid or developing solvent and called as the moving phase. The components of the mixture to be separated migrate at different rates and appear as spot at different point on the paper. In this technique, a drop of the test solution applied as a small spot on a filter paper and the post is dried. The paper is kept in closed chamber and the edge of a paper is dipped into a solvent called developing solvent. As the filter paper gets the liquid through its capillary axis and when it reaches the spot of the test solution, the various substances are moved by a solvent system at various appends. When reached or travel to a suitable length, the paper is dried and spots are visualized by suitable reagents called visualizing reagents. The movement of substance related to the solvent is expressed in terms of RF values, that is migration parameter. What is migration parameter? The migration parameter, the position of the migrated spot on the chromatogram are indicated by terms such as RF, Rx and Rm. The R is related to the migration of solid front from solvent front. Rf equal to distance travelled by the solute from the origin line, distance travelled by the solvent from the origin line. R is a function of a partition coefficient. It is constant for a given substance provided the conditions of the chromatographic system are kept constant with respect to temperature, type of paper, duration and direction of development, amount of liquid in the reservoir, humidity, etc. That is quality of paper in this case. Nature of mixture, temperature and the size of the vessel in which the operation is carried. Rx means in some cases the solvent front runs off the end of filter paper, the movement substance is expressed as Rx. Rx equal to distance travelled by the substance from the origin line, distance travelled by the standard substance from the origin line. Rm. The term Rm is additive and is composed of the partial Rm values of the individual fractional groups of atoms in molecule. The formula is Rm equal to log of 1 bar RF minus 1. Coming to types of paper chromatography. Ascending chromatography, when the development of the paper is done by allowing the solvent to travel up the paper, it is known as ascending technique. In the ascending mode of development, the paper is suspended so that the lower edge is below the level of the solvent and the solvent moves up via capillary action. An alternative to suspending the paper was to form a self-supporting cylinder from the paper. As with TLC, multiple developments with either the same or different solvent was used to improve resolution, although time taken for each development must have made this especially tedious to perform. Both ascending and descending technique have been employed for separation, but descending technique is preferred if the RF values of the various constituents are almost same. Coming to descending chromatography, when the development of the paper is done by allowing the solvent to travel down the paper, it is known as descending technique. The advantage of descending technique is that the development can be continued indefinitely even though the solvent runs off at the other end of paper. The descending method of the chromatogram development was that originally proposed by Martin and his co-workers. In descending paper chromatography, the upper end of the paper is immersed in a solvent contained in a suspended trough so that the so initiated as in the ascending mode by capillary action is sustained by gravity and will continue so long as there is solvent to feed it. This had the useful consequence that a sheet of any length could be used. In addition, the solvent could be allowed to run off the end of the paper, thus extending the chromatographic run if needed to improve resolution or enabling compounds to be eluted from the paper and collected for further experiments. The results obtained for a particular sample solvent system combination run in either ascending or descending mode were usually similar. However, the latter was generally faster. Ascending descending chromatography. It is a hybrid of two techniques. The upper part of ascending chromatography can be folded over a glass rod, allowing the descending development to change over into the descending after crossing the glass rod. Circular radial paper chromatography. This is also known as circular paper chromatography. In this technique, a circular filter paper is employed various materials to be analyzed or placed in a center. After drying the spot, the filter paper is fixed horizontally on petri dish possessing solvent, so that tongue of paper dips in a solvent. When solvent front has moved through a sufficient large distance, the components gets separated, forming concentric circular spots. Two-dimensional separations on paper. Where separations were not achieved in a single development, it was often possible to achieve the desired result using a second solvent system of different composition and development in a second dimension at 903 to the original direction of chromatography. Two-dimensional paper chromatography was described by Kunsden, Gordon and Martin for the separation of 20 amino acids, but was subsequently widely employed. An additional possibility was the use of paper chromatography in one direction with electrophoresis, both high and low voltage in the second. Indeed, there are numerous examples in the literature of either chromatography followed by electrophoresis or electrophoresis followed by chromatography. Coming to procedure for paper chromatography. In paper chromatography, choice of the proper chromatographic techniques. The choice of technique is depends upon the nature of substances to be separated. Choice of filter paper, whether the paper is being used for quantitative or qualitative analysis, whether it is used for analytical or preparative chromatography, whether substance used are hydrophilic or lipophilic, neutral or charged species. Proper developing solvent. The choice of this depends upon the simple fact that RF values should be different for different constituents present in mixture. A solvent or mixture of solvent which gives RF 0.2 to 0.8 for sample should be selected. The solvent are listed in order of increasing polarity in table 2. Coming to RF values, the distance a substance travels related to the distance the solvent travels is called the RF value. The RF values can be calculated by measuring the distance of the substance from its starting point in millimeters as well as the distance the solvent traveled from its starting point in millimeters, then dividing the substance distance by the solvent distance, that is RF equal to distance the solute moved over distance the solvent from moved. The equation is, it does not matter if the solvent moves 100 mm or the RF values of a substance will remain the same. For example, the average RF value for a dye called methylene blue is 0.50 that means if the substance moved 5 mm, the solvent moved 10 mm. It also means if the substance moved 50 mm, the solvent moved 100 mm. Application of paper chromatography. This technique is widely used for qualitative analysis of inorganic, organic and biochemical interest. It is also useful in analysis of mixtures of amino acids and mixture of sugars. Given the importance of paper chromatography in its heyday, a list of its application covers all types of analytes including proteins, peptides, amino acids, poly, oligo, dye and monosaccharides, natural products, sterols, steroids, bile acids, pigments, dyes and inorganic species. To conclude, chromatography is a method of analysis by which components of a mixture are separated by redistribution of molecules of mixture between two or more phases. It is used for purification, separation and preparation purpose. Phases in chromatography are stationary phase and mobile phase. One of the method of classification of chromatographic technique is based on the state of matter of stationary and mobile phases. Another method of classification is based on principles. General classification contains different well-known methods. Different principles of chromatography are adsorption, partition, ion exchange, exclusion. Diagnostically important method of chromatography is paper chromatography, which is used for separation of serum amino acids. Other methods are clinically useful. Paper chromatography is a method used to separate mixtures into their different parts. Paper chromatography has been most commonly used to separate pigments, dyes and inks. To do paper chromatography, you need paper with a lot of cellulose fiber and chromatography solution, which is usually made from a mixture of water and alcohol. Paper chromatography works because inks usually contain several different colors. Ink manufacturers mix different amounts of primary colors like blue, red and yellow to make many other colors. During paper chromatography, we can separate basic colored inks that contain different ingredients because some inks are more attracted to the paper and some are more attracted to the alcohol or water. Thank you everyone.